Greetings, everybody. Let's take a look at partial fraction decompositions. So what we have with partial fraction decompositions, we basically want to decompose a rational expression into a sum of proper rational expressions. Now, what do I really mean by that? Proper rational expressions and whole polynomials. Now, kind of how does this work? It's really similar to what we did with fractions in elementary school. Now, when we had a fraction that looked something like 23/5, okay, that what would happen in that case, we said that this was going to be improper because the numerator was bigger than the denominator. And so we knew then what we had to do. We just did long division. So we said 5 goes into 23 4 times. So 5 times 4 gives us 20. We subtract and we have 3 as the remainder. Now, we know we're done at that point because the remainder is going to be smaller than the divisor. Okay, so we're dividing by 5, so 3 is smaller than that, so we know that we're done. And what this really let us do with the division algorithm was we could say that 23 was then going to be 5 times 4 plus 3. So that when we had our fraction, 23 divided by 5, that was going to be 5 times 4 plus 3 divided by 5. Well, we could say that was going to be 5 times 4 divided by 5 plus 3 divided by 5. So our 5's canceled out at that point, and we were left with 4 plus 3/5. And so what happened, we then wrote this as our mixed number of 4 and 3/5. Okay? The same thing kind of happens with polynomials as it does with integers. So now, let's, for comparison, suppose that we had a polynomial 5x squared minus 17x plus 13 all over x minus 3. So now, with polynomials, we know that we can measure the size of a polynomial by the degree of the polynomial. And so what we have here, we have something that is going to be of degree 2 on top and degree 1 on the bottom. So the numerator is bigger than the denominator. And so what we have then is an improper rational expression. Well, all that means is that we can do polynomial division on it. And just for polynomial division, we can do something similar to what we did with our long division. But we do things with looking at the largest terms and taking things down 1 degree at a time. So we first start to ask ourselves the question of comparing the leading terms. So we look at x, and then we look at 5x squared. And we say, all right, what do I need to multiply x by in order to give me 5x squared? And so for that, what I need is 5 times x. And so what I then do, I say I've got 5 times x and 5 times 3. So I multiply the 5x times the polynomial that I have. That gives me 5x squared, my leading coefficients match. So 5x and then 5x times 3 gives me a minus 15x. And then what do I do? Just like in long division, I'm going to subtract those two polynomials. And so what this gives me is that my 5x squareds cancel out because that's how I designed it, so those go away. I have a minus 17 minus a minus 15, so minus 17 plus 15 gives me a minus 2x, and then my remaining terms just come down. So at this point, now I'm kind of looking at, am I to the point where I'm finished? Well, not quite yet, because I'm looking here, I see degree 1, because that's just a linear polynomial. This is a linear polynomial, so it's a degree 1. So they're both degree 1, they're the same size. If they're the same size, I can keep going. I want to go until this degree is smaller than the degree of the polynomial I'm dividing by. And so with that, I can go one more. I can say, once again, what can I multiply x by so that I end up with a negative 2x? Okay, and quite naturally, the question with that is going to be, I need a negative 2. So now I take the negative 2 and I multiply by the x, and I take the negative 2 and I multiply by the negative 3. So that's going to give me a negative 2x. Negative 2 times negative 3 gives me a positive 6. And then I subtract those two polynomials. So in subtracting those polynomials, my negative 2x minus a minus, so plus 2x, those cancel out. 13 minus 6 then gives me 7. So now I have something that is going to be degree 0 because it's just a constant, degree 1 up here, and so yes, the remainder is now smaller than the numerator. And so what this really means is that I could take this 5x squared minus 17x plus 13, just like I did before. So 5x squared minus 17x plus 13, and it will be x minus 3 times 5x minus 2 plus 7. And if I want to confirm that that's actually true, I could multiply that out. If I did that, what would happen? I would have a 5x squared, 5x, and then a minus 2x, a minus 15x, a plus 6, and then a plus 7. So what do I end up with? 5x squared minus 17x plus 13, exactly as I'm supposed to have. So that what happens in my rational expression now, and so now what happens when I just replace this expression, so I have my 5x squared minus 17x plus 13, I rewrite that as x minus 3 times 5x minus 2 plus my 7, and I can decompose that so I can divide each term by my x minus 3 plus my 7 over x minus 3. And so now my x minus 3 as terms cancel out, and so I am left with 5x minus 2 plus 7 over x minus 3. And sure enough, what I end up with is a whole polynomial and something that looks like a true polynomial, a proper rational expression. So I've gotten a whole polynomial part and a proper rational expression, and I've decomposed those into kind of their component forms. So now let's suppose that we've got a rational expression that looks like x squared plus 4x plus 7 divided by x squared minus 6x plus 5. Okay. Well, again, kind of looking at this, I'm seeing I've got a degree 2 in the numerator, and I've got a degree 2 in the denominator. So really, those are the same size, which tells me that, again, I have a whole polynomial part that's contained in this. And so what I have to do then is to find that whole polynomial part, I am doing long division. So I have x squared plus 4x plus 7. Well, I'm looking at what do I need? I need to multiply something by x squared to give me x squared. So what's going to do that job? Well, the answer is 1. So if I do 1, so 1 times that polynomial, and what happens, I have x squared minus 6x plus 5. And then I subtract my polynomials. My x squareds go away. So I have 4x minus a minus, so 4x plus 6x, which gives me 10x. 7 minus 5 is going to give me a plus 2. And so what happens now is similar to my improper fractions. I have a whole polynomial of 1 plus my remainder, 10x plus 2, divided by x squared minus 6x plus 5. So for this one, we're just kind of separating it out. But we can actually go further than that because the denominator will factor. If I look at how that factors, I really have x minus 5, x minus 1. So that's going to give me my x squared minus 6x plus 5. And so the question is, can I take this proper rational expression and separate it further? So can I find something so that this expression will look like some constant over x minus 5 plus some other constant that I don't know over x minus 1? And the answer is yes, we can find these a's and b's, and so how do we go about doing that? So really what it comes down to with our partial fraction decompositions, when we factor the denominator, then we are going to get one of two things. So the denominator, when we factor it, will either give us linear factors, or it will give us irreducible quadratics. Now, when we say irreducible quadratics, we can't factor those things in a nice way. That irreducible quadratics, basically we have so irreducible quadratics kind of means that we have non-real complex roots. Okay? So when we have kind of these non-real complex roots, we can't factor those things with real numbers, so we can't turn them into linear terms. Okay, and kind of when, as a reminder of maybe whenever that happens, if we've got a quadratic, ax squared plus bx plus c, remember that we had the discriminant. And the discriminant was our b squared minus 4ac. If our discriminant was positive, then we knew we had two real roots. If our discriminant was 0, then we had one real root of multiplicity 2, and if our discriminant were negative, then that meant things were irreducible. So I had non-real complex roots. Okay. So this is kind of one check that we've got to decide when something is going to be irreducible or not if we're just given a polynomial. Okay, so what happens when we factor our denominators? One of these two things. Now we have maybe these things to higher powers, maybe our multiplicities of these factors go up, and we'll see how to deal with that. All right, so let's say that we factor our denominators, and really we just have some expression, so some polynomial in the numerator, and then in the denominator, we've got x minus alpha to the n power. Okay, so that's how our denominator factors. What we do then in our expression, we really have, for every power of n, we're going to have a term in our sum. Okay, so for every power of n, we will have a term in our sum. And so those will be just our increasing powers of that factor. So we'll have a factor with x minus alpha. We'll have a factor of x minus alpha squared, plus all the way up to factors of x minus alpha to the n. Okay, so those are the denominators in our partial fraction decomposition. But then, because our factor is a linear factor, so factor is a linear factor, then our numerators will be constants. So in our numerator, now we've got a total of n constants that we would have to figure out. We would have a constant a1, have a constant a2, all the way out to a constant a sub n. One for each power of, one for each factor in our multiplicity, it's in our denominator. So when we have some power of our irreducible quadratics, a similar thing happens that if we have that to some power, then our denominators are still going to be the increasing factors of n, so we're still going to have n terms in our sum.